All right, so in this video, we are going to talk about the dynamics of circular motion. So if an object is executing circular motion, or more generally, if it's following any type of curve, then there has to be some force or some combination of forces pointed in the radial direction. Radial direction means towards the center of the circle or the curve. So this particular force or this particular combination of forces is called the centripetal force. Okay, now let's look at an example. Suppose I have, let's take a simple example of something that's going around in a circle. Suppose you've got this stone or some object which is sitting on a frictionless surface, right? So the screen here is the frictionless surface on which the object is sitting. And let's say that you've tied this object by a rope to a fixed point O, right? All right, you keep the rope taut and then you give the object a whack. Maybe you give it a push and the object starts going around in a circle. If the surface is frictionless, then it'll just keep going in a circle forever. So this is a very simple example of circular motion. Now, we just talked about how when an object is executing circular motion, there has to be some force which is pointed towards the center of the circle. Can you identify what that force is here? The answer is that force is simply the tension of the thread. That force is simply the tension of the thread. Okay. And so tension is the force that's ensuring that the object keeps on this circular track, right? What would happen if you snap the thread? If you snap the thread, you know that the object will no longer have any reason to follow the circular path. And so if the thread is snapped in this position, then the object will just fly off keep moving in the direction of the instantaneous velocity it had at the moment the thread was snapped. So when the thread is snapped, the velocity of the object was tangent to the circle, and so the object would just keep moving in the tangential direction, in the direction of whatever velocity it had the instant the thread was snapped. So in order for the object to keep moving in a circle, it has to have there has to be a force which is pointed towards the center of the circle. There can be many other examples of many other examples of objects going in a circle. So just imagine the sun. Just imagine the sun and a planet orbiting the sun. Can you tell me what is the what is the force which keeps the planet in its circular orbit? The answer, obviously, is the gravitational force. So there has to be some kind of force which is pointed towards the center of the circle in order for the object to move in a circular path, right? So this force which points towards the center of the circle is called the centripetal force. Centripetal force. The word centripetal literally means center seeking in Latin. So that's why it's called centripetal, because this force always points towards the center of the circle. Now, there's a very important conceptual issue which I must clarify here. When I talk about forces, I gave you two examples, the tension force, the gravitational force. These are actual, honest-to-God forces. These are real forces, physical forces. What about centripetal force? Centripetal force is not an actual force. It's a generic name for any force that's responsible for keeping the object going in a circular path. So here, in the first example, the role of the centripetal force is played by tension. So here, the tension provides the centripetal force. And in this second example, gravity plays the role of the centripetal force. So hopefully you can see that centripetal force is not a particular force, not an actual force, actual physical force. It is whatever, it is a generic name for whatever force is pointed towards the center of the circle and is keeping the object going in a circular path. Right? Let's look at another example. Suppose you have a circular track and you have a car that's going in a circle. And this is our top view of the car. The car is following the circular track. Can you tell me what is the centripetal force? Which force is playing the role of the centripetal force in this case? Which is the force that's always pointed, that's acting on the car and is always pointed towards the center of the circle? If you think about it, you'll realize that it's the force of static friction. Why is it static friction? It's static friction because the wheels of the car, if you consider the point of the wheel which is in touch with the road, that point is instantaneously at rest. That point is not sliding against the road, right? So the friction that applies is the static friction. You know that kinetic friction applies when two objects are sliding against each other. But in the case of the wheel rolling on the ground, the point instantaneously in touch with the ground is not sliding against the ground, right? You can just roll a circular object on your tabletop and see that the lowermost point of the circular object, which is in touch with the tabletop, that is not sliding against the tabletop when it's rolling along, right? That is instantaneously at rest. And so the friction that applies is static friction. And so in this case, static friction provides the centripetal force. Okay. Now, you know that static friction, what's the formula for the maximum force of static friction? So the formula for the maximum force of static friction is μs times the normal force, right? So it depends on the normal force. It also depends on the coefficient of friction, right? And the coefficient of friction is a property of the two surfaces involved, right? Let's say that there is an oil slick on a certain part of this track. So when there is oil on the road, then the coefficient of friction between the tires and the road is going to be much lower. So in that case, the centripetal force is going to be, the friction will not be able to provide the same amount of centripetal force, right? Because the friction force will be much lower, the maximum force of static friction will be much lower, and so friction might not be able to provide the necessary centripetal force needed to keep the object going in a circle, and so in that case the car would not proceed in a circular path because it's not enough centripetal force. Friction is not able to provide enough centripetal force, and in that case the car would just slide off like that. Okay. All right. So hopefully it's clear to you that centripetal force is whatever force is acting towards the center of the circle, and it's the force or forces that's responsible for keeping the object going in a circular path. And many different forces can play the role of centripetal force. Okay, now let's analyze a situation in which an object is going in a circle, and we are just going to apply Newton's second law. So let's go back to our very first example where we had an object which was sitting on a frictionless surface, and the object was going in a circle like this because it's tied to a rope which is attached, the other end of the rope is attached over here at the point O, and so the object is going in a circle, right? So let's apply Newton's second law to this object. When you apply Newton's second law, the first step is to identify all the forces. So what are the forces acting on this object? The real physical forces, there's only one, and that is the tension. All right? And since the object is moving in a horizontal plane, we are not going to worry about the forces which are in the vertical plane. So in the vertical plane, there is just the weight of the object acting down and the normal force acting up, and those two are equal and opposite, and so they don't play any role in determining the horizontal motion of the object. So we only are only considering the forces in the horizontal plane. So there is tension, right, which is acting towards the center of the circle, and that's the only force that there is. So let's apply Newton's second law. Newton's second law says that net force F net equals mass times acceleration, right? Typically, this is a vector equation. And what you do is you break up the forces into components and then apply Newton's second law along each direction. So in the problems that you've done earlier in this chapter, you would break up the forces into x and y components, apply Newton's second law in the x direction, Newton's second law in the y direction, and get the equations that you need in order to solve the problem. All right, now when an object moves in a circle, there is a very convenient choice of axis for resolving forces. So let me explain that to you. The way you choose your axis in that case is you take one axis in the radial direction. Hopefully the meaning of radial is clear to you. It's in the direction of a radius, and the other axis in the tangential direction. So that's perpendicular to the radial direction, in the direction of the tangent. So when an object is going around in a circle, the radial and the tangential directions are the two directions along which you resolve your forces. So we have the tension force here, which is already in the radial direction, so there is no need to resolve it into components. And we can write down Newton's second law now in the radial direction. So in the radial direction, let's write down Newton's second law. Now you might remember when you're setting up Newton's laws, you need to have a sign convention. So you need to choose your signs. You need to be clear about which direction is the positive direction, which direction is the negative direction. There is an excellent sign convention that goes with this choice of axis, and that sign convention is radially inwards is positive. Plus VE is just my shorthand for positive. So any vector, whether it's a force or an acceleration or a velocity, if it points in the radially inward direction, we are going to give it a positive sign, right? So, all right, so now we are all set to write down Newton's second law. So the net force in the radial direction, there's only one force, that's the tension. And what sign should it get? It should get a positive sign because it points radially inwards, is equal to mass times the acceleration. Now the acceleration for an object that's going in a circle is always the centripetal acceleration, AC. Now you might remember from chapter 3 that when an object goes around in a circle, its centripetal acceleration is given by the formula AC is equal to v square divided by r. V is the speed of the object as it's going in a circle, speed of the object on its circular path, and r is the radius of the circle. So t in this case becomes equal to mv square divided by r. And that is Newton's second law in the radial direction. Okay, so that's just an example of applying Newton's second law. I'll do one more example of applying Newton's second law for an object that's going in a circle. Now consider an object. Let's take the same object, but now we are whirling it around in a vertical circle. So the object is going in a circle, but the circle is vertical. You can just imagine tying a stone to a piece of thread and then just swinging it around in a vertical circle. So this is a vertical circle. Let's apply Newton's second law at any point. Let's just apply Newton's second law when the object is maybe somewhere over here. Maybe over here. It doesn't matter. I'm just choosing a random place on the circle. So when the stone is over here, we want to apply Newton's second law. Okay, so let's first identify the forces. If you look early on in this PowerPoint, chapter 4 and 5 PowerPoint, there is a discussion of the steps involved in calculating, in applying Newton's second law. The first step is to identify all the forces. So what are the forces acting on the stone? The forces are the force of gravity, which is acting down like this, mg. Then there is the tension force, which is acting along the thread like this. Okay, and now we want to find out, so those are the only two forces. One question that I often ask in class is, what about the centripetal force? Is that also a force acting on the stone? The correct answer is no, because the centripetal force is not an actual force. It's just a generic name for whatever forces are pointed towards the center and are keeping the object in a circular path. So the centripetal force is not an actual physical force, as I've clarified earlier. I'm just mentioning this so many times because a lot of people seem to have that misconception that the centripetal force is another force that you should also consider. Okay, now we have our forces. We want to resolve the forces into components and apply Newton's second law. That's what we want to do. So we saw earlier that a good choice of axis when an object is going in a circle is the radial direction and the tangential direction. So we're going to break up the forces in these two directions. Now the tension is already in the radial direction, so nothing to do there. The mg is not along our two axes, so we need to make one component in the tangential direction like this and another component in the radial direction like that. And let's say that this angle is theta. So that would mean by geometry this angle is also theta. And so this component would be mg sine theta, and this component would be mg cosine theta. All right, so we've broken up the forces into components, and now we are ready to apply Newton's second law. Now, before applying Newton's second law, we need to also be clear about our sign convention. So what is our sign convention? Again, we know what our sign convention is when an object is going in a circle. The sign convention is radially inwards should be taken to be the positive direction. So our sign convention again is just radially inwards is positive. Okay, so let's apply Newton's second law in the tangential direction first. So what force do I have in the tangential direction? Mg sine theta. And I haven't really come up with a sign convention for the tangential direction. It doesn't matter what sign convention you choose for that. You can just choose this direction that in which mg sine theta is pointed. Just take that to be the positive direction. So you get mg sine theta is equal to mass times whatever acceleration the object has in the tangential direction. And I'm just going to call that at. Right? So that's your equation. And what can you do with this equation? If you wanted to find the tangential acceleration of the object, you could easily solve for it from this equation. In fact, the tangential acceleration, so this equation implies that the tangential acceleration is g sine theta. Okay, so that's what you get from there. let's apply Newton's second law also in the radial direction. So in the radial direction, we want to, there are two forces. We want to take the net force, which means that we have to be careful with our signs. So mg sine theta should get a negative sign because it's pointed radially outwards, and t should get the positive sign because it's pointed radially inwards. So our equation would be t minus mg sine theta is equal to mass times the centripetal acceleration. Right? Okay. Okay. Now the centripetal acceleration is, so why centripetal acceleration? Because the object is going in a circle. So for an object going in a circle, it has to have an acceleration pointed towards the center, and that's the centripetal acceleration. Okay. The formula for the centripetal acceleration, you know, is v square over r. You can plug that in as well if you want. So t minus mg sine theta is equal to mv square over r. V would be the instantaneous velocity of the object at the position shown, and r is the radius of the circle. And this is the equation that you get from the radial direction. So I just showed you how you can apply Newton's second law to an object going around in a circle, and that's pretty much all there is to it. Okay, now let's look at this quantity. So that's what I mean in the third bullet point on this slide. Choose axis along the radial and the tangential directions. Newton's second law in the radial direction becomes F net equals mass times A centripetal, which can also be written as mv square over r. All right, now the quantity mv square over r can be interpreted as the amount of force necessary to keep an object of mass m moving at a speed v constrained to a circular path of radius r. So let me just clarify that. So we are getting this mv square over r on the right hand side of our equations, the radial equations. We also got that over here when we looked at the static force, the tension force, when the tension force was providing the role of the centripetal force. So we have some forces on the left side, and that's equal to mv square over r when you write down Newton's second law in the radial direction. Now mv square over r can be interpreted as the amount of centripetal force necessary to keep the object moving with velocity v and in a circle of radius r. So if you want an object of mass m, let's say of mass m, if you want an object of mass m moving with velocity v in a circle of radius r, then the amount of centripetal force necessary is given by this quantity mv square over r. Let's look at an example of that. Let's go back to our car example. So our car was moving in a circular path. Let's say that the car is describing, this is our car. The car is describing a circle of radius r. R, I don't know, is maybe 100 meters. And the mass of the car, let's say, is 1000 kgs. And let's say that it's moving at with a velocity of 10 meters per second, which is approximately 20 miles per hour. If you want to quickly go from meters per second to miles per hour, the actual conversion factor is 2.2, but you can just round that to 2. So if you have a certain meters per second, then you want to find out what's the ballpark approximate miles per hour that is, then you just times it by 2. So 10 meters per second is approximately 20 miles per hour. Okay, so how much, okay, so you know that for the car going in a circle, can you tell me what is providing the centripetal force? We just discussed that a little while ago. The force that's providing the centripetal force here is friction, static friction, right? So if you calculate the quantity mv square over r, that will tell you how much centripetal force, or how many newtons of centripetal force the friction needs to provide in order for this to be possible, in order for the car to maintain this particular circular track at this particular speed, right? So let's go ahead and calculate that just as a concrete example. So that's going to be 1000 times 10 squared, which is 100, divided by 100. I can't really do arithmetic, so I take the easiest numbers possible. So it's 1000 newtons. So the friction has to be able to provide 1000 newtons in order for the car to be able to continue that circular path. So that's the interpretation of mv square over r. It tells you how much centripetal force is necessary for a car to be able to follow that particular circular path at that particular speed. So if the car is staying on that circular path, that means friction is able to provide that speed. But suppose there's an oil slick, and we talked about that a little while ago. Suppose there's an oil slick, then the friction is going to be lower, right? Because the coefficient of friction is lower. So in that case, the maximum force of static friction might be less than 1000 newtons. So friction is just not able to do it. It's just not able to provide 1000 newtons. And so in that case, the car will not be able to remain in that particular circular track, and it will just start drifting off the circular track. Okay. All right. So I have a nice illustration of that over here. So that's what I explained in this bullet point, the second bullet point here. If the agencies providing the centripetal force can supply mv square over r newtons, then the object will stay on the circular path. And if not, the object will no longer stay on that circular path. And I just wanted you to watch this video. So keep an eye on the guy with the blue shirt. So these guys are spinning this this merry-go-round, and the centripetal force is here being provided by the normal force of the railings and the friction of the guy's shirt. Obviously, those are not able to provide enough centripetal force, so the blue shirt guy has moved on to a different circular track. Now they're desperately trying to reduce the friction, reduce the velocity, but it didn't succeed. Anyway, so you can watch this video yourself later on. All right, the next thing that we're going to discuss is, so in the PowerPoint I have a couple of examples. Yeah, these are both important examples, so we'll work through both of them. Okay. All right, so I'll let you read the example on this slide, the passenger in the Ferris wheel, and see if you can set it up yourself. After that, we are going to discuss it. So a passenger on a Carnival Ferris wheel moves in a vertical circle of radius r with constant speed v. So here you've got the Ferris wheel, and there is so this is the seat, and the passenger is seated over here. All right, and we are considering two positions: one when the seat is at the bottom, and second when the seat is at the top. Okay. Find expressions for the force that the seat exerts on the passenger at the top of the circle and at the bottom of the circle. So let's start with the bottom of the circle. Can you tell me which force they're asking for? Which is the force that the seat exerts on the passenger? The answer is, it's just the normal force, right? So the normal force is the force exerted by any surface when an object is placed on that surface. So the normal force is what's being asked for, Fn. What's the other force? What other forces are acting on the person? The other force acting on the person is the weight mg. And those are the only two forces acting on the person when they're at the bottom. And the Ferris wheel is moving, the person is moving with a velocity v over here. Okay, so let's apply Newton's second law to the person. We know how to resolve our forces. We know that when an object goes around in a circle, you resolve the forces in the radial and the tangential directions. So one would be the radial direction like this, and the other would be the tangential direction like that. So all the forces are in the radial direction. We have a sign convention ready, which is that radially inwards is positive, right? So let's write down Newton's second law. See if you can write it yourself. So Fn should get a positive sign. So this is at the bottom. Fn should get a positive sign because it's radially inward. Mg should get a negative sign because it's radially outward, right? That's the net force, F net, equals mass times the centripetal acceleration AC. And that is Newton's second law. Please make sure that this equation is absolutely clear to you. So we can just plug in the form for AC, which is v square over r. So Fn minus mg is equal to mv square divided by r. R is the radius of the Ferris wheel, radius of the circular path. And so from here you can solve for Fn. So Fn is equal to mg plus v square divided by r. Okay. Now, all right. Okay. Let me just ask you one question. Suppose you were plugging numbers into this equation. What number should you plug in for g? Should you plug in g equals positive 9.8 or should you plug in g equals negative 9.8? Think about that for a moment and try to answer the question first and then resume the video. So pause the video and think about that, then resume the video. The correct answer is you should plug in positive 9.8. And why is that? Because the negative, when you do minus 9.8, the only thing that the negative signifies is the direction of that acceleration. So we have already taken direction into account when we put the minus sign right here. So we've already taken the direction into account over there. So there is no need to put a negative sign anymore after that point. That the direction has already been taken into account. So if you were to plug in numbers to get a numerical value for Fn, you would do positive 9.8. All right. Okay. So that's how you would get the normal force at the bottom. Let's do the same thing at the top. And you can do this yourself. There's nothing new here. What are the forces acting on the person? The normal force is the force exerted by the seat. So that is going to be upwards again. And the weight of the person will be acting down. So not any different from before. Those are the forces. All right. Now, let us apply Newton's second law as usual. So Fn is now in the radially outward direction, so it should get a negative sign, and mg is in the radially inward direction, so it should get a positive sign. So mg minus Fn is equal to mac, which is mv square divided by r, right? So you can solve for Fn from here. So Fn is equal to m g minus v squared over r. So the question is, in which position, okay, so that answers the first part of the problem. The second part of the problem is asking, in which position will the person feel heavier than usual? Now, you probably know this, but your own sensation of your weight is not mg. So if you're standing somewhere, you have a sense of how heavy you are, right? But that sense that you have is not from mg itself. It's from the normal force. The normal force is the thing that you actually measure, that you actually perceive, right? Why? Because when you're standing, how do you have a sensation of your own weight? You're standing on the ground, right? So your feet are being pushed against the ground. So the nerve endings at the bottom of your feet can get a sense of how much push is coming from the floor, right? And so what is that force of the floor pushing back on you? That is the normal force. So you are, when you perceive your own weight, it's the normal force that you're perceiving, right? Okay, so now, in which case will the normal force be greater? So clearly the normal force will be greater at the bottom, because if the wheel were not moving, Fn would just be equal to mg. But with the Ferris wheel moving, it's mg plus something extra, v square over r, right? So the normal force will be greater than the person's weight, and the person will feel heavier. Whereas at the bottom, at the top, the normal force would be less than the person's weight, because it's g minus something, and so the person will feel lighter at the top, right? There's a very interesting application of this. When I say that when Fn is greater than the person's weight, the person will feel heavier, but every part of their body will be heavy. Every part will seem heavier. So for example, if the person is holding a 5-pound, thick 5-pound physics book or chemistry book, that book will seem heavier by exactly the same amount. If they try to lift that book, that book will feel heavier, right? Now, every part of the person's body will seem heavier, right? What is the heart of the person doing? It's pumping blood into the person's brain if the person is sitting upright, right? So the blood will seem heavier as well. So if the velocity is very high and Fn is much greater than mg, then it would be very difficult for the person's heart to pump blood into their brain. Now, in a Ferris wheel, the velocity is very small, so it's not going to be an issue at all. But there might be situations where the velocity is very large. What is a situation like that? One situation like that is a fighter jet, which is executing a vertical loop like this. So let me see if I can draw a fighter jet. Okay, that's not a bad fighter jet. Okay, so you have a fighter jet, and it's executing this vertical loop, right? Let's say that the radius of this loop is 500 meters, and the jet is moving at 140 meters per second, which is like 280 miles per hour. That's fairly slow for a fighter jet. So 140 meters per second, you have the velocity. So in that case, when the pilot is at the bottom of the loop, what is the normal force on the pilot? You can use the same formula that we just derived. So Fn would be equal to mg plus v square divided by r. So let's just calculate this part. Let's just calculate the v square over r. So it's going to be mg plus 140 square divided by 500. If you do 140 square divided by 500, let's see what that comes to. 140 square divided by 500. So that's approximately 40. It's 39.2, so it's approximately 40. G is approximately 10, right? So G is approximately 10. So this is approximately mg plus 4g approximately, right? So m times 5g. So the normal force felt by the person is 5 mg, or 5 times their weight, right? So this situation is called 5 Gs. So we say that the pilot is subjected to 5 Gs, which means that their body weight is 5 times what they normally perceive So their body weight, the normal force is 5 times their body weight, or their own perception of their weight will be 5 times what it normally is. So as you can imagine, this is a very, very uncomfortable situation, and most people would pass out at 2 or 3 Gs. Fighter pilots are trained to still remain uh, to not pass out and keep their brain still active at 5 Gs or high Gs like this, 5 or 6 Gs. Because for most people would pass out, because remember that the person is feeling 5 times as heavy as they are. So that means their blood is 5 times as heavy as it normally is. As far as the heart is concerned, the heart will find that the blood is 5 times heavier. So the heart has to work much harder in order to pump blood to their brains. And for normal people, the heart will just fail to do that, and the person's brain will not receive blood, and the person will just pass out, right? So fighter pilots are specifically trained. They get a tremendous amount of cardio training, and they are trained to withstand high Gs like this, so that they don't pass out and they can still make crucial decisions when they are subjected to such high Gs. Okay. We're going to do one more example, which is the second last example on the slide. So please take a look at this example and see if you can figure it out. This particular example often comes up, so it's important to understand it. So what's happening here is that there is a bucket which is filled with water. Okay. So the bucket is filled with, half of it is water, right? And then you're swinging the bucket in a vertical circle. You're swinging the bucket in a vertical circle. And you can try this yourself. I actually do this demonstration in class. If you swing it fast enough, you'll find that the water doesn't spill at the top. It's pretty amazing to watch. The water doesn't spill at the top. And you can try it yourself if you have a small bucket handy. The water will just stay at the top and not spill. So the question is asking, but if you do it slowly, then the water will spill. So you have to go pretty fast. So the question is asking, what is the minimum speed the bucket should have at the top of the circle such that the water doesn't spill, right? So to analyze this, let us just do the same thing. Let's apply Newton's second law. So consider the forces acting on the water, right? So one force is the weight of the water acting vertically downwards, mg. Another force would be, can you tell me what's the other force? The other force would be the normal force which is exerted by the bottom of the bucket, right? Now the bottom of when the bucket is upside down, the bottom of the bucket is above the water. So the normal force would be acting down on the water, right? So the normal force acts down like this. So you have two forces acting on the water. One of them is its weight, mg, and the other one is the normal force, both of which are pointed downwards. Let's apply Newton's second law to the bucket. So again, we have to break the forces into radial and in the radial and tangential directions. Here everything is in the radial direction, so there's no problem. Our sign convention, as usual, is radially inwards is positive. So Fn plus mg, both of these are in the radially inward direction, is equal to mass times A centripetal. Or in other words, Fn plus mg is equal to mv square divided by r, r being the radius of the circular path followed by the water. So now the question, so that's an equation that's generally true when the bucket is flung around in a vertical circle. The question is asking for the minimum speed at which the water will not spill, right? So when the water is about to spill, what can you tell me about the normal force? When the water is just barely making contact with the bottom of the bucket and it's just hardly making any contact at all. So what can you tell me about the normal force? The answer is the normal force will be practically zero. So in that case, you get the minimum. If you plug that condition in, you get the minimum velocity. So if Fn is approximately 0, then mg is equal to mv square over r, and that v would be the minimum velocity that the bucket can have for the water to not spill, right? So that is the velocity at which the normal force is just a hair above 0. Okay, so if you can solve for v minimum from here, square root of gr, and this is a useful result which often comes in handy. All right, so that concludes our discussion of centripetal force. Basically, the idea is that whenever an object goes around in a circle, there has to be some force or some combination of forces which point towards the center of the circle. These forces are called centripetal force. This combination of forces is called the centripetal force, and it's responsible for keeping the object in a circular path. And when you apply Newton's second law to an object going around in a circular, following a circular path, then the net force is equal to mass times A centripetal, and A centripetal, as you know from chapter 3, is v squared divided by r, and so you get an equation where net force in the radial direction is equal to mv squared over r. And that's all there is to it. Okay.